suppose the system is growing. So you have a solution like this, and from the experiment, suppose you get these data points, okay, and you fit a best exponential curve, and what this experimental data will tell you, what information you are going to get from the experimental data. So you assumed this model, and you got a solution, and you also got experimental data. Now how do you fit the experimental data to the model you have developed? That's exactly right. So the k value you don't know to start with. You just got the solution assuming arbitrary k constant value, but you don't know the value of the constant. So you need to do the experiment and find what's the best k that fits the data. And there is a better way of doing this than plotting the exponential curve. Does anybody know what's that way? Yes?
Plotting a log.
That's exactly true. So if you plot on log scale, if you plot log of n and time, so in this equation, if I take log of n is log of n0 plus at. Do you follow this equation? So now this is a straight line. This is a straight line. So you get this. Now your data points are like this, and you fit a straight line, and from the slope gives you the constant k. Okay? And does this problem of fitting the best straight line through these experimental points remind you of any homework or exam problem?
Pseudo-inverse?
Pseudo-inverse, yes. What was the midterm problem? Do you remember the midterm problem? What was that? That was exactly like this. So you have some experimental data and you wanted to fit a straight line. Okay? Now what happens, suppose you plot in log and then you don't get this behavior. Suppose your data looks like this. Now, looking at the data, you see that it's very difficult to draw a straight line. It seems more curved than a straight line. Do you agree? So, and if such a thing happens, what do you do? Suppose you started with the kind of simplest assumptions, you solve the equation, and you end up with this model, but when you try to fit to the experimental data, you see that the straight line is not the best fit. Probably a curve is even better. And then what do you do? One thing, you can try to do the experiment again, and there might be errors in the experiment, so you might also need to consider the error bars in the experiment. But what else you can do in terms of the modeling?
K wouldn't be a constant.
Yeah, you're thinking in the right direction. So it might happen that the model is not so simple. You might have a term like this. Because before doing the experiment, nobody told you that you need to have this linear growth. Okay? You could have a term which is proportional to n square, and that's not going to give you such simple exponential growth or exponential decay. Okay? So that's how typically computational modeling in biological systems work. Like you start with a very kind of simple assumption, set of assumptions, right? The simplest model often, and then solve the equation, try to fit the experimental data. And if you see big deviation, then you go back and question the assumptions of the model. Okay? So for example, in the simple example, you question whether this linearity assumption was correct. And to remedy the situation, you probably try the best or simplest possible thing you can do. So you add a n squared term and see then whether you can fit the data. Okay? But more complicated models means there are two things. One, analytical solution may not be possible. Okay? So it's always nice to have such an analytical solution, because you know how exponential functions look, or cosine functions look, or sine functions look. Whereas if you don't have analytical solution, you don't have good insight sometimes. Okay? So that's one problem, that you may not have analytical solution if you try to be more realistic, more rigorous. The other problem is now you have more parameter values. And the risk and the problem here is, once you start getting more and more parameters, you can always play with those parameters and feed the experimental data. And there's a big danger. So you can cook up a model. You can think of a model with 3 different or 4 different terms and 4 different constants. And you can always play with those parameters and feed the experimental data. But nobody really tells you whether that model is correct, because you have so many free parameters in the model. Okay? So that's another danger of having too complicated model with too many terms. But sometimes you cannot avoid it. If your experimental data tells you that no way this model is right, the exponential growth is right, you have to do something. Okay? So you get a feel of how you try to model biological systems and then go back and forth between theory or modeling and experiments. And that's a big challenge in today's biology and biomedical engineering. And in biomedical engineering, there are 2 major applications. One is to describe basic biological processes like this, cell biology of, say, cell growth, those kind of things. And the other challenge is when you try to design biomedical systems like MRI or X-ray, all those kind of imaging systems or other instruments, you often have to do quantitative measurements. So in MRI, you need to think what should be your magnetic field to detect a specific thing. Okay? And those things are described often by either differential equation or partial differential equation. So you need to know how to solve those equations to describe those instruments in biomedical. So I'm going to show you, not right now, but let me kind of briefly write some of the applications we are going to cover. Or you want to create a drug which is inhibiting receptor ligand binding. Okay? There are a lot of drugs which inhibit receptors or signaling molecules. And you want to design such a drug, and you have to come up with a number, like what's the concentration you want to apply. Okay? And those kind of calculations should emerge from this ODE or PD modeling. So some of the applications which I'm going to cover, one is this cell growth, death problem. And I wrote these in my handout. You can see the order may be different, the order I'm writing right now, receptor ligand binding. And then, so this is the problem where suppose you have receptors on the cell surface and ligands are binding, and you want to calculate receptor plus ligand. You want to know how many complexes are formed at some time t. So if you start with some initial R and initial L, the complex at time t you want to calculate. So that's one application. Then the other application will be motion of magnetic moment in a magnetic field or MRI. And then motion of intervertebral disc. Okay, so there are 2 kind of you have a region between two vertebrae, and if you apply a force there, how this thing moves, the intervertebral disc. And this is an example from biomechanics. So probably you have different interests, and some of you are more cellular and molecular, and these are applications from cell and molecular applications of biomedical engineering. This is more imaging, MRI, imaging system, and this is more biomechanics. And I'm going to come back to these applications in the next lecture after I develop the formalism to model these systems and solve those equations. So there are two challenges. One challenge is how do I model, how do I describe the system? And the second challenge is how do I solve? Okay. So for example, here the first challenge was what to write here. Should I write Kn or should I have delta n squared? So this is the first level challenge. What terms you want to include, what do you want to do here? And the second challenge is, can you have a solution? How do you solve the equation? So if it's just Kn, you have a nice exponential solution. If it's delta n squared, then it's already more complicated than that. Okay? So there are two major issues. So how do you model the system and how do you solve such a system? Tell me some of the applications you have seen of ODE. Anyone? What? You must have seen some applications. Fluid flow, yes, that's more PDE, is that right?
In circuits, we had to, on our midterm we had to solve for inductor voltage and current as a function of time. That had to use differential equations.
Sure. Yeah. Little bit of formalism which you might be familiar with already. Order and degree of an ODE. I'm not going to do too much of this. Order is the highest derivative. So this equation d2y dt2 plus a dy dt united b plus cy equals 0. So what's the order of this equation? 2, because the highest derivative is second order. So the order of this equation is second degree. And what is the degree? Do you know what degree is? Do you know the definition? The definition is simply the highest power of the highest derivative. Okay, so what's the degree here? 1. So if this was, if I write d2y dt2 square plus b dy dt plus cy equals 0. So in this case, order 1, degree 1, and this is, what's the order? So the order is 2 here, not 1. Order is 2 because the second degree. Order is still 2, and the degree is also 2 because now I have a second power. Yeah.